Okay, good morning, everyone. Lecture number 5 today. Let's pick up with resistive circuit analysis. We stopped here yesterday, equivalent resistance, and we solved two examples, A and C. Did you look at B and D? Except that the resistor is drawn diagonally on the schematic. It is in series and parallel. Okay, so as always, if you want to find REQ, total equivalent resistance between any two pairs of terminals, you always start at the farthest end. So in example C, if we start at the farthest end, sorry, example B, if we start at the farthest end, what do we see? R4. R4 has two terminals. If you look at those two terminals, where are they connected? What is the next resistor after R4? As you move towards your terminals of measurement, R3. If you look at R3, R4 terminal is connected to R3 right here. And the other end of R4 is also connected to R3. So what can we say about R3 and R4? They're in parallel, absolutely. So example C can also be drawn like this. There's R1, R2, R3, and R4. What I'm doing is, since I have the resistor on a diagonal, I'm going to redraw the circuit in a way that makes sense to me. And so I'm going to stretch out this node, the bottom node. So I'll take this and I'll stretch it out. And so R3 is now going to be vertical right here. Does that make sense? Again, if a schematic looks complicated to you, you can always redraw it in a way that makes sense to you. Yes. Oh, yes. Thank you. B, C is on the left. Okay, so as I was saying, you redraw the schematic in a way that it makes sense to you so that you can better analyze it. So all I'm doing at this point is I'm taking R3 and I'm stretching this out. So when I stretch this out, I'm pushing R4 towards the right. And then I can clearly see R3 and R4 are in parallel. Okay, so from this point on, it's quite easy to find REQ. The next step in this would be to combine R3 and R4 in parallel. I would say R3 parallel with R4. R3 in parallel with R4, which would then be, let's redraw one more step. So I have R1 here, R2, and then I will call this as R5. R5 is the parallel combination of R3 and R4. So you reduce it one step at a time. Again, if you practice this long enough, a light bulb will click on at some point in time, and you can simply look at a circuit and easily determine which resistors are in series and in parallel. But when you're first starting out, if you're not sure, you take it step by step. R3, R4 is now R5, or named as R5, the parallel combination of R3 and R4. Then what can we say about R2 and R5? They are in series, quite obvious, right? So if they are in series, you can take it one step further. Call this R6. R6 is simply R2 plus R5. And then finally, our total REQ is relationship between R1 and R6. REQ is measured between the two terminals on the left. I always need coffee. Do you guys need coffee too? R1 and R6 parallel. So REQ is R1 parallel R6. It would be nice, right? If Cal Poly had like a coffee machine in every classroom. Okay, so let's recap the steps. We had R3 on the diagonal. I just stretched out the node at the bottom, made it vertical, so it makes sense to me. I can see R3 and R4 are in parallel. I combine it to form R5, which is then in series with R2. That gives me R6. And as a last step, I can see R6 is in parallel with R1. So my total REQ is R1 parallel R6. Let's take a 10-second pause. Let me know if you have any questions. Does it make sense to everyone? Okay. Then D. D again is rather straightforward. Actually, it's easier than B. This time I'm going to take the diagonal resistor and stretch it out to the left. If I stretch it out to the left, I get this circuit. REQ is measured at the open terminals. And so in this case, I get REQ equals, again, start at the farthest end. R2 and R1 are in series, so R1 plus R2. And that series combination is in parallel with R3. So parallel with R3. And that's it. All right, think over it. Let me know if you have any questions. So the values are given in all four problems. We'll go ahead and do it as a practice, and I'll post the solution in these same notes. Okay, post the solution in the same notes. So why do we do this? Well, we use this technique, again, reducing a bunch of resistors down to one single resistance. We compress the circuit down to one single element, and we can find the voltage or the current flowing through that circuit. And then we expand it back up again in the reverse order, and we can find voltage and current for every single resistor that's in the circuit. And that technique is known as series parallel equivalence. Series parallel equivalence. Again, remember I said every analysis technique is going to be built step by step. So we first learned about elements in series and parallel. We learned how to combine it in series, learned how to combine it in parallel. Then you applied both techniques to a larger circuit. You reduce that circuit down to one single resistance, and then we introduce a source in it, and we come up with a technique called series parallel equivalence. So simple 3 steps. The first step is you take the large network of resistors and you determine whether it can be reduced to a single resistance or not. Okay. If a question asks you to apply this technique, 100%, the circuit can be reduced. Now, I'm not going to trick you by asking you to reduce a circuit that cannot be reduced. All right, so reduce the network of resistors to a single resistor, apply Ohm's law, determine the voltage or determine the current. If you are given a voltage source, you find the total current in the circuit. If you are given a current source, right here in this example, we have a voltage source. So if you're given a voltage source, you find the current. If you are given a current source, then you find the total voltage in the circuit. Once you have that value, you expand the circuit back up in the exact reverse order. And you can find values for the voltages and currents for every single element or every single resistance. Okay, so let's take a look at this example. This example, hold on. You have three resistors, R1, R2, and R3. At the farthest end, what do we have? R2 in parallel with R3. So as a first step, I'm going to redraw the circuit like this. Now take out your calculators and do this calculation with me. What is the parallel combination of R2 and R3? 30 parallel with 60. Oh, sorry. What do we have? So this, let's call this R4. R4 is R2 parallel with 60. One over 30 plus 1 over 60. What do you get? 20? Yeah. So if you have two resistors in parallel, an easy technique is take the two resistors, the product of the two divided by the sum of the two. So in this case, it's 30 times 60, it's 1800 divided by 90. I'll repeat it again. If you have two resistors in parallel, when you solve that equation, reciprocal of the sum of the reciprocals, it simply breaks down into the product of the two divided by the sum of the two. So in this case, 60 times 30 gives you 1800 divided by 90, 30 plus 60. And so R4 is 20 ohms. Did that make sense? Two resistors in parallel. Just an easy technique. Okay, so we had 20. What do you notice about that 20 in relationship to the values of R2 and R3? It's smaller. So when you add up resistors in series, it's not quite obvious because our brains already know it, but we don't think about it, right? Because when you add something to a quantity, we always expect it to be bigger. So a series combination of resistors has a value that will always be bigger than the largest resistor in that network. At the same time, when you have a parallel network of resistors, the total R equivalent for that parallel resistances will always be smaller than the smallest resistor in that network. In this case, the smallest value between R2 and R3 is 30. So your REQ cannot be more than 30. That's an instant check. If it's more than 30, then there is an error in your calculations. Okay, so always keep that in mind. If you're trying to reduce a parallel network of resistors, that final answer should always be smaller than the smallest resistor in that network. 20 is smaller than 30, so that that tells me that my value is on the right track. Make sense? Okay, so it's just an important thing to keep in mind. All right, then this is Vs, and I reduce this further. It's in series. I get R1 plus R4, 10 plus 20, go to 30 ohms. Actually, let me point out the first step that we should have done. Sometimes I forget that these things are like fundamental for us, so we keep doing it for so many years. Sometimes forget to actually do one important step in this case. We are trying to find REQ, right? But we are trying to find REQ from the perspective of the source. Okay, in the previous slide, we learned about reducing a bunch of resistors down to one single resistance. So in this case, the terminals are with Vs removed. So you remove Vs, and then you find REQ from the perspective of the source. So that's the step I was forgetting. You remove Vs, so you remove the source, and you find REQ between those open terminals. So then you start at the farthest end, then you reduce the network as you move towards the source. Now, this step is not important for you to show, when you solve for in a quiz or in an exam. You don't have to show this step, but this is something I like to teach students. So, when you're first starting out, if you're not comfortable reducing a circuit directly, then you should do this. Remove the source and then find REQ between the open terminals. Okay. Is this technique, do you learn this in physics? Okay, all right. So now I have Vs 90 volts. I assume a current that flows in the circuit. I, total current flowing in the circuit, right? Voltage is given, so now I find the current I. Which direction would you choose for that current? Going clockwise or counterclockwise? I actually just drew it. So here's the answer is correct. Answer is clockwise, but here's where the passive reference configuration comes into picture. Remember, I said current always goes from high to low, from plus to minus. So for resistors, it always goes from high to low. Capacitors always goes from high to low, plus to minus. Whatever polarity of your voltage is, high end goes towards the negative, except when it is a source. When it is a source, it goes from minus to plus. Okay, it's supplying energy. So when you're supplying energy, it goes from minus to plus. Point of entry, if the current enters the negative terminal, power is negative. Remember? Otherwise, our equations would never balance out. So we are assuming a direction for the current in the circuit, but our assumption is based on logic, and the logic tells us that a power supply is supplying current. So it goes from minus to plus. If it goes from minus to plus, then my current is going clockwise. And so the arrow points here. That's the passive reference configuration. Make sure each one of you understands this, okay? For the components, resistors, capacitors, and inductors, the current always goes from high to low, from plus to minus. If it's a supply, whether it's a voltage supply or whether it's a current supply, source, supply or source, it always goes from minus to plus. So we don't know the direction. Yes, go ahead.
If that were a battery, then it would be
It'd still
opposite,
be the same.
basically.
It would still be the same thing because a battery is still a source.
Okay.
So, yeah. So anything that supplies voltage, anything that supplies current is a source, and a source will always have current going from minus to plus. So we assume the direction of the current based on the logic. Logic tells us, again, passive reference configuration, the source is supplying current, so it's going from minus to plus, and that means the current goes in the clockwise direction. Now we apply the voltage polarity to the resistor in the opposite direction, in the opposite way. Current enters a voltage and it causes a voltage drop. Again, as I said, for a resistor, capacitor, inductor, current goes from high to low. So our clockwise current I is entering the resistor from the top. So what is the polarity of that terminal? Is it plus or is it minus? I hear some murmurings. It is plus. Again, otherwise, our equations would never balance out. So it's plus and minus. And I will call that V. Let's call it, let's see, R1, R2, R3, R4. Let's call it R5. Should have written it down. That doesn't make sense either. R5 is equal to R1 plus R4. So this voltage I can write as VR5. VR5. Yes. So for a resistor, capacitor, and inductor, passive components all, current always goes from high to low, goes from plus to minus. So conversely, if you take the exact same statement, we can also state if a current always goes from high to low, that means that when a current enters the terminal of that element, that point of entry is plus. So high to low is plus to minus. It always goes from plus to minus. So if you have a voltage sign across a resistor, plus and minus, current will always go from plus to minus. On the other hand, if you already know the current direction, then we can say point of entry is plus and point of exit is minus. It's two sides of the same coin. If current goes from high to low, if current goes from plus to minus, then again, the other side of that is that if we have given a current, then the point of entry of that current is plus, exit is minus. Does that make sense? Okay, so now VR5. The other thing I want to point out, are they in series or are they in parallel? They are in series and they are in parallel. Two components connected to each other. That's the only time when we can say both of them are in series and they are in parallel. Okay. So if they're in parallel, you have the same two nodes. This is the exact same node that is shared between the voltage source and the resistance. Okay. And if it's in parallel, the voltage across those two nodes will remain exactly the same. So what can I say about VR5 and VS? They're the same. So the value of VR5 is the same as VS. Or you can say VS is the voltage that's being applied to that resistance. Okay, that's the voltage that is being applied to that resistance. And then once we reduced it to a single resistance, it's a simple case of applying Ohm's law. V equals IR. You have one voltage in that circuit, you have one resistance, and you have one single current. And that's it. We apply Ohm's law and we figure out what the value for I is. So I is simply Vs divided by R5, 90 divided by 30, so 3 amps. Make sense? Any questions? Okay, so now, now that we have the value for current, think about this. Current's going from here. It's traveling along the path. What is the current that goes through R1? Doesn't have any pathway, so current I is still the current that's flowing through R1. So the current flowing through R1 is still I. We have I, we have R. We can find voltage across R1. Again, Ohm's law, right? 3 quantities. If you have any of the 2 quantities, you can find the third. So now we expand the circuit back up again in the reverse order. So in the reverse order, meaning this. I is flowing through Vs, it's flowing through R1, and it is flowing through R4, which is the parallel combination of R2 and R3. So before writing this down, I'm going to explain it. I is the current that flows through Vs, through R1, and through R4. I know the value of I know the value of my resistors, R1 and R4. Apply Ohm's law, V equals IR. I can find the voltage drop across R1, and I can find the voltage drop across R4. You guys with me so far? Now, since I know the voltage across R4, I take it one step further in the reverse order. The reverse order would be here, which is R2 and R3. If my voltage across these 2 points, VR4, once I calculated, and I know that voltage, it's the parallel combination of R2 and R3, meaning the same voltage appears across R2 as well as R3. Make sense? And again, Ohm's law, I have voltage V, I have value for resistance R2 and R3. I can find the current flowing through each one of those. Do the steps make sense? Again, I reduce the circuit towards the voltage source. Once I found the current, I'm expanding it back up again, step by step. Yes. You can do that too. So you apply KVL, and you find the value that way. So the question being asked was, once we have the voltage across R1, can we just subtract it from 90 and find the voltage? And absolutely, that's the verification step. That's the verification step. You apply KVL and you find the voltage across R4. So let's do it. Continuing from VR5, I have I. VR1 would simply be I times R1. So 3 times, what is it, 10? 30 volts. Okay, 30 volts. Then my R4 is 20. So VR4 is I times R4. 3 times 20 gives me 60. And again, KVL, or just as a check, 30 plus 60 gives me 90. So my answer should be correct. And then if I want to find IR2, VR4 divided by R2, 60 divided by, what is it? 30. 2 amps. And IR3 is VR4 divided by R3, 1 amp. And you can do a cross check. Law of conservation of energy applies. Okay. A source is supplying some power, it is supplying some energy. The total energy being supplied by the source has to equal the total energy being absorbed by the resistances in that circuit. That means if the source is supplying 90 volts, the sum of the voltages across the resistances should equal 90. So if you apply KVL, across the loop, I do get minus 90 plus 30 plus 60 equal to 0. And you apply KCL at the top node or at the bottom node, doesn't really matter. I have I entering this junction. Logically, IR2 and IR3 will be going down. Oh, the voltage polarity for VR5 is also, plus and minus. So we get the current direction for R2 and R3 as going from top to bottom. We can get it from there, or we can also assume it from the direction of I. If a current is entering a junction, it just stands to reason that, again, logic dictates that the current would follow that pathway. And so if it's coming from left to right, it's going to follow that direction and go from top to bottom. So one current entering the junction, I, 3 amps plus 2 of them leaving, thus verified. All right, does it make sense? This is, of course, a simple circuit, simple example. So there's only 2 steps. We combine resistors in parallel and we solve it that way. Let's take a 10-second pause, think over it. Let me know if you have any questions. Any questions at all? Did every step make sense? All right, let's move a little bit faster then. This one, A. Remove the voltage source and analyze the circuit to find Req between these terminals, right? And we start at the farthest end and we move towards the front end. So if you want to find Req, and I start at the farthest end, I see R4 is in parallel with R3 is in parallel with R2. Someone calculate this and give me the answer, please. This would be 1 over 40 plus 1 over 30 plus 1 over 20. Not Req, sorry. Actually, yeah, let's just do it in one step. Req. The parallel combination of this is in series with R1. So it's plus R1 plus 10. So what is the parallel combination? 9.23. This is plus 10, right? Without the 10. Yeah, okay, thank you. So Req is 19.23 ohms. Does anyone else have the same answer? Same, thank you. So now I can find the total current I. The current direction is already given to us, so we don't need to worry about it. Total current I is simply 20 Vs divided by Req, 1 point something. How much is it? 20 divided by 19.23, 1.05, 1.05 amps. All right, 10-second pause. Any questions? Straightforward enough? I want to say easy enough, that's my phrase, but then easy enough is not always fair to the students. So straightforward. Typically, I don't, if I give examples or homework problems might have some sideways, but for my exams and in-class examples, there are no like twists or turns or tricks. Pretty much be straightforward. Okay, so once we have I, we can see I is the same current that's flowing through R1. So I1 is equal to I 1.05 amps. Then that same current I is also flowing through the parallel combination of R2, R3, and R4. Okay, and since all three of them are in parallel, the same voltage appears across all three of them. Okay, same voltage appears across all three of them. As a side note, the voltage that appears across the parallel network or any parallel network is a result of the values of all three of them acting together. Okay, so it's not as if you're applying 20 volts to this network and then it's just 20 to all of them. No. If I take R4 out of the circuit, then the voltage would be different. Okay, so a voltage that appears across a parallel network of resistors is a result of all of them working together. And that's why voltage across parallel nodes is exactly the same. So let's find the voltage across R1. So now we can solve this in two different ways. We can find voltage across R1 and find voltage across the parallel network by applying KVL. Or we can find the current flowing through, well, we already know the current. We can find the voltage that appears across all three of these. So we can say, and I'm going to call this R5. VR5 can be calculated as I times R5, which is 1.05 times 9.23. Or alternatively, I can do it as Vs minus, apply KVL, I can get Vs is equal to VR1 plus VR5, right? So VR5 would be Vs minus VR1. Let me scroll. It should be 20 minus 10.5. .5 volts. I'm pretty certain this also should give me 9.5 volts. So 9.23 times 1.05, what do we get? that is fine. 9.69. Because we took 2 decimal places, 9.23. If we had gone longer, maybe 4 or 5 decimal places, these values would have been closer. So VR5, just to recap as a step, R5 is the parallel combination of R2, R3, and R4, right? So the voltage that appears across here, I call it VR5, and the voltage that appears across R1, VR1. Again, current is going from left to right, point of entry is positive, point of exit is negative, and I keep the same polarity convention going forward for the other 3 resistors. So I apply KVL. I know Vs is 20. 20 minus VR1 should give me VR5. That comes out to be 10.5. 1.05 into, yeah. If we take more than 2 decimal places in the resistance, this current would be slightly different. Instead of 1.05, would have a few more other more accurate numbers. Okay. Anyway, so we apply Ohm's law and we can find value for VR5, or we can apply KVL, Vs is equal to VR1 plus VR5, and find the voltage that way. So in one method, we get 10.5. The other method, or the other technique, we get 10.69. Sorry, 9.69. Right, 9.5 versus 9.69. In a quiz or an exam, I will not deduct points. I will give, if one student gets 9.69, the other student gets 9.5, I will get full points to both. Okay, it's fine. One note about the method. This method is series parallel equivalent, right? Series parallel equivalent. So when I ask you to solve a problem using this technique or this method, you will show me this method, right? Where you reduce the resistances down to one single resistance and you apply Ohm's law. But within this method itself, within this series parallel technique, you can apply Ohm's law or you can apply KVL, which is fine. Does that make sense? Right? The larger method is series parallel analysis. So you use that series parallel equivalent analysis method. You show me that you can reduce to one single resistance, and then you can expand it back up again. You can show me a circuit schematic for every step, or you can just write up the equations like these. It's absolutely fine. And within this method, when it comes to the smaller steps, you can have Ohm's law, you can have KCL, you can have KVL. So different students might choose different methods, which is fine. Okay, so now once we have VR5, we can find I2, I3, and I4 simply by applying Ohm's law. Make sense? IR2 is VR5 divided by R2. IR3 is VR5 divided by R3. And IR4 is VR5 divided by R4. Okay. Any questions? Okay, let's move to example B. There are 2 ways to solve this. Since we are learning about series parallel analysis technique, I will solve it using that first, then I will show you the other technique. Common sense technique, actually. You don't even need to be an engineer to solve it. All right, so let's see. This has a current source, 2 resistances in series. Combine it together. Combine it together. So this is what, 20. This is 20. Another fun fact, well, not fun fact, but another easy technique to keep in mind, if you have a parallel network of resistances and all of them are the same value, the answer is simply the resistance value divided by N, the number of resistors. So in this case, 20 is in parallel with 20, two resistances, 20 divided by 2, 10. That is the answer. And you can try that with any number of resistors. 20, let's say you have 3 20 ohm resistors in parallel. The answer would be 20 divided by 3. So parallel resistor was out to be 20. Two resistors, product of the two, 20 times 20 is 400, 400 divided by 20. Oh, 400 divided by 40 gives you 10. So this time we have a current source. So if you have a current source, you want to figure out what the voltage is across that network. And let's call that voltage Vs between those two nodes. This is exactly the same node. This is also exactly the same node. Okay, so 10 volts, sorry, not 10 volts, 2 amps times 10 gives me a value of Is times Req, 2 times 10 gives me 20 volts. 20 volts is applied across both branches of the resistances. So my I1 is 20 divided by 20, gives me 1 amp. And I2 is also let's call this R5 and R6. R5. So again, from the top, R1 and R2 are in series. Since they're in series, I can combine them. The resulting resistance, I label it as R5. And R3 and R4 again are in series. I label that as R6. R5 and R6 are both 20 ohms. Combine those together in parallel, I get a resulting Req as 10 ohms. 2 amp current source being supplied to a 10 ohm resistance gives me a voltage of 20 volts. 20 volts applied to R5 and R6 gives me 1 amp each. Any questions? Now let's look at the common sense answer. You have current IS going up top. It's going up top, going towards the right, and it splits in two. Goes through I1 and I2, right? Current source of 2 amps is being split in two, and it's being split in exactly equal halves, 20 and 20. So 2 amps split in half, 1 and 1. That's the answer. All right. Practice problem C. And let me know if you have any questions. In C, R3 and R4 are in series, which would then be in parallel with R2, which would then be in series with R1. Practice and solve. If you have any questions, you let me know. All right, we'll end class here today. We'll pick up here again on Friday. Yes. Sure.